Have you ever stopped to think about the simple magic behind resizing an image or, making a game character suddenly grow huge? Well, today, we're pulling back the curtain on a core concept of computer graphics, 2D scaling. Right? Whether you're pinching to zoom on a photo on your phone or you're watching a boss in a video game suddenly loom over you, you are seeing the exact same powerful idea at work. And today, we're going to break down exactly how it all functions. So, let's start with the basics. What is 2D scaling? Well, to put it simply, it's the fundamental process of resizing digital objects right there on your screen. At its very core, scaling in computer graphics is just about changing an object's size. We can make it bigger, that's enlargement, or we can shrink it down, which we call reduction. It's this really basic transformation that underpins so much of what we do on our devices. And the 2D part of the name is super important. We're operating on a flat, two-dimensional plane, basically your screen. Every object has a width, which runs along the horizontal x-axis, and it has a height along the vertical y-axis. Scaling is all about playing with those two values. All right, so how does a computer actually do this? This is where we get to what I like to call the magic numbers that make it all happen. These magic numbers are officially called scaling factors, and there are two of them. We've got Sx for the horizontal or x direction, and Sy for the vertical or y direction. These two little numbers are literally the complete instruction set for how much an object should change its size. And the rules are incredibly simple. If a scaling factor, either Sx or Sy, is greater than 1, the object gets bigger in that direction. And if the factor is between 0 and 1, something like 0.5, the object gets smaller. It's really as simple as that. And the math behind it? It's surprisingly simple. It's just multiplication. To find the new coordinates of any point, which we'll call x prime and y prime, you just take its original coordinates, x and y, and multiply them by those scaling factors, Sx and Sy.
Okay, let's make this real with a quick example. Imagine a single point on our screen, and it's located at the coordinates 2, 3. We'll just call it point P.
Now, let's say we want to make our object twice as wide and 3 times as tall. So we set our scaling factors. Sx is going to be 2 and Sy is going to be 3. We just plug these right into our formulas. The new x is the old x, which was 2, times our scaling factor 2, which gives us 4. And the new y is the old y, 3, times its scaling factor, 3, which gives us 9. And boom, there's our result. The new point, P prime, is now at coordinates 4, 9. By applying those scaling factors, we've actually moved the point farther away from the center. Now just imagine doing that for every single point in a shape. That's how you resize the entire thing.
Okay, so this brings us to two really distinct types of scaling. And the choice between them is what determines whether an object keeps its original shape or it gets all stretched out into something totally new.
So first up, we've got uniform scaling. This is where the scaling factors, Sx and Sy, are exactly the same. The object grows or shrinks, but its proportions stay absolutely perfect. Then you have non-uniform scaling. This is what happens when Sx and Sy are different, and it's how you get those classic stretching and squashing effects that completely distort an object shape. All right, so scaling one single point is one thing, but how does this work for entire images or complex characters? And how do developers handle this efficiently? Let's scale up our thinking a bit. The principle is exactly the same. It's just applied over and over and over. When you scale a shape, whether it's a simple triangle or a really complex image, the computer is just applying that same multiplication formula to every single point that makes up the object. That's how the entire thing resizes all at once. Now, in professional graphics programming, doing this for every point individually would be incredibly slow. So instead, developers use a really powerful mathematical tool called a scaling matrix. This little grid holds our Sx and Sy values, and it lets the graphics hardware perform the scaling calculation for thousands or even millions of points almost instantly. This thing is the engine that makes real-time resizing possible. So why does all of this matter? Well, because this isn't just theory, right? You see and use 2D scaling literally every single day. No, seriously, think about it for a second. Resizing an image in Photoshop? That's scaling. An animated character that shrinks or grows, that's scaling. Pinching to zoom on a map on your phone, or watching an enemy in a video game suddenly get huge, it is all 2D scaling at work, my friend. The big takeaway here is this. 2D scaling is one of those silent, fundamental pillars of our digital world. So the next time you resize a window or watch a character transform on screen, you'll know the secret. It's all just powered by this simple, elegant bit of multiplication. It's just a perfect example of how really complex, magical-looking visuals can be built on simple, elegant math. Which, leaves us with a pretty fascinating question to think about. What other simple mathematical ideas are shaping the digital world on your screen right now?